Hello everyone. Today we're going to go over LeetCode problem 337, House Robber 3. So basically what's going on in this problem is it's a binary tree problem. So I'm just going to go over the problem statement here. So the thief has found himself a new place, like a neighborhood, and he wants to maximize his gains in the robbery. So essentially what's going on here is that a thief can only rob houses that are not connected to each other. And that is because if he robs two houses that are, then the police will be called on him. So he'll be busted. So just to go over the first example right here, for the thief cannot rob 3 and 2 because those are adjacent, or they're directly connected, but he can rob 2 and 3. So we can go over the potential robberies that can be performed on this one. Again, the first one that I said 2 and 3, so 5, and then the other option is 3, 3, and 1, which is 7. That's the winner. The thief can also rob 3 and 3 or 3 and 1, any combination of these, but they just can't be connected. And now we can go over example 2 here. And I'm going to jump into the whiteboarding session for that one. So this is example 2. And you can see I have an alternating row of colors. And I've actually expanded on example 2 here. So what the thief can do is he can rob 3 and its grandchildren, so 3, 1, 3, 4, 1, or this row of houses and their grandchildren, 4, 5, 2, 5, 7, 9, 6, 5, 4, and 3. So if you add up all the sums for each color, for this and this, you get a sum of 12, and for the greens, you get a sum of 50. So that's the clear winner here. So yeah, just to go over the solution here. First and third rows, the blues, 12, and second and fourth rows, the greens are 50. So that's the one, that's the group of houses that the robber would go for. So now we're just going to jump into kind of quote-unquote dumb solution. So it works, but it's extremely slow. So what we have here is a solution where the nodes are essentially alternated. The descendants are alternated. So here we start at the root. Let me change my colors here to green. All right, so here we start at the root first step, and we go and we iterate for the left node, and we go over the grandchildren. So we get the sum of the grandchildren's so you get the sum for the left grandchildren and the sum for the right grandchildren, and you add it all to value or val, and you essentially find the max. So there's the max of two groups of values. The first, of course, is the value of the root here plus the value val, which you just found, which was of the grandchildren, and you add those up. That's one group. The second group is the other alternation, which is the robbery values of left plus right. So that's one group, and when you find the max of those two, you get the best choice. So again, for this tree right here, that would obviously be 50. So with the green group, which is the winner, that would be this one right here, because of course you're not doing the root, you're doing the second alternation. So now we're going to go over a slightly more complex solution, but this one is the most optimal. So for this optimal solution, we're going to use the first example tree. This one right here. So to go over this, we're going to just run through the code. And you can see I have a lot of notes written here. So let's walk through it. So when we start out at the root, you calculate the left array. And for this you have to make the recursive call for node 2, so this one. And you can see I have the notes written down for there. Let me zoom out a little bit. So for 2's left array, that's going to be, and I should rewrite this. This is going to be a array of size 2 with both values set as 0. And then the right array, we're going to make the recursive call for node 3c, and the notes are here for that. So the left, again, this is going to be an array of size 2 with values 0, 0, and same thing for the right. Yep. And then you calculate the res array, the result array. So that is the math.max of left 0 and 1, which is 0. And then result index 1 is the value of that node plus left 0, right 0. So we have 3. And this one is 0 plus 0. Index 1 is 3 plus 0 plus 0, which is 3. So now we go back to the call for node 2x. And here we have, so we've calculated our right array, and that is 0, 3, which is what we returned here. So now we calculate the result array for node 2. So let's run through that again. Math.max of left 0, left 1, that's 0 plus 3, which is 3. And the result array at index 1 is 2 plus 0 plus 0. Again, it's the value of that node plus left 0, right 0, and those are both 0. So that you get 2 from that. So this is the result array that this operation or this function call returns. So now we're back at our operation, our initial function call at the root, which is 3a. And you can see here we have array with values 3, 2. So that is done. Now we can go to the calculation for the right array. And so again, it's going to be something very similar to what we just did. We can quickly go through the function calls again. So the left value again is going to be 0, 0. The right value, we make a call for 1y. 1y is 0, 0, 0, 0 for its left and right. And of course we get result at 0 is 0. Result at 1 is 1 because its own value is 1. So we return that here for the call at 3b. And so let's calculate the result array for 3b. At index 0, it's 0 plus 1 equals 1 because math.max left 0, left 1, 0. math.max of right 0, right 1 is 1, so 0 plus 1 equals 1. And then the result array at index 1 is that current node's value, so 3. And then left 0, right 0, which are both 0, so 3 plus 0 plus 0 equals 3. So now we're back at the initial function call, and the right array here is 1, 3. So now we have to calculate the the last result call, many result calls, or not calls, I'm sorry, calculations. So at index 0, we do math.max of the values in the left array. So that's going to be 3. And then math.max of the values in the right array, which is, again, 3. 3 plus 3 is 6. And then for index 1, we are doing the roots value, 3 plus left 0 plus right 0. So 3 plus 3 plus 1 equals 7. And of course, the correct answer is 7. All right, so now that we've run through the solution, and this is kind of what I asked myself, the first time I ran through the steps of the algorithm, was what exactly is this result array, and how do you actually end up getting this answer? Because when I did it the first time, it wasn't really immediately clear to me what was going on. So essentially, I'm going to go over what the first, what index 0 means, and then what index 1 means. So I'm going to draw another tree here. So we have X, Y, and Z. All right, so index 0 and index 1. So what index 0 means is you're not robbing the root. Okay, so you're not robbing the root, and you're going, you're basically focusing on the children of the root. So these two. Let me draw that better. So these two. So you're not robbing the root, and then it's basically the max output of, let me move this, of two things. First, let's focus on the left child. Max. Left child. You either rob the left child or you don't rob the left child. So you have two choices here, and you're basically finding out which one yields the highest results. And same thing for the right child. Rob right child and rob left child. Let me make these markings a little clearer. So
don't rob right child.
Yeah, sorry, I forgot. Yeah, I'm erasing the wrong things. All right. Don't rob right child. So this symbolizes Z, symbolizes Y. So this is what res 1 is. So you have two values here, and if you don't rob the left child, that could possibly lead higher results. Same thing for right child. So if you find the max of both of these, that could yield you the highest valued solution, of course, when you're not robbing the root or the current node that the function call is focusing on. All right, so res 1 is kind of the flip-flop of that. So you are robbing the root. And let me actually redraw the diagram to make it a little clearer. X, Y, Z, and then you're not focusing on the children at all. And here's where it would go into like grandchildren territory. I'm going to draw that to make it a little more clear here. So you are robbing the root. You add that to the sum of res 1. And okay, so yeah, you're adding the root and I'm going to draw little bubbles for these because these kind of symbolize function calls. And it is the output of not robbing the left child. So it's really just the left child's grandchildren. And same thing for the right. Okay, so you're not robbing the children because of course that would violate one of the givens of the problem. You can't, these are related, so you can't rob X's children directly. So these kind of just symbolize function calls, and yeah, this is the value of not robbing the left child, but you can rob its direct descendant. And this is not robbing the right child, but you can rob its direct descendant, and so on. So conceptually, that's what's going on here. That's res 0, that's res 1, and when your operation goes all the way back to the root, like we did right here, in that final operation, what we found was that robbing the root plus the max values of the robberies of root's grandchildren, 3 and 1, yielded the highest results versus doing this operation here, which did not yield, it yielded 6. So that is the house robbery 3 problem. All right, and thank you for watching.